All right, welcome back to episode 3 of Evans Imagines Negative Mass Antimatter. We'll kind of go over the homework full screen, and then we'll get into the regular class and in the PowerPoint mode like regular, just to give you a little more hello time from Evans and make it more like an actual class with a teacher and stuff. Although I guess lecturers don't really do this as much, and the first thing I'm going to do is tell you the first and fourth questions you should just look up. I'm not going to go through them with you like, you're a baby. You can just go Google them. They're cool. They're fun. And see what happens when you calculate the expectation value of p squared or x squared with the p or x operator when you construct the p or x operator out of raising and lowering operators. It's pretty cool. So apply it to random states. You'll see what happens. It picks out a very specific state. So it's cool. And it tells you a whole class of answers to questions. So pretty awesome. Number 1. Number 4, similarly, I found that out when I was preparing this class a while ago. Yeah, it's very strictly a perturbation theory treatment when you're doing path integral formulation of quantum mechanics. So yeah, fun to read those and understand those questions, but we're not going to go over them in detail. What I will go over in some detail is the Einstein Podolsky and Rosen paper. So there's this paradox, and it's not exactly clear what their concern is when you read the paper if you already believe quantum mechanics, because you're like, okay, fine. Yeah, all that's fine. You could have a hidden variable, I guess. Try to figure it out. There's some, is it Bell's theorem? Somebody's theorem that you can't have a hidden variable if you have something else, but they didn't have that back then. So that's not what anybody's talking about in the EPR paper. The point was that Einstein wanted the world to be complete. He spent the last 23, 40, whatever, however long he was in academia after he did general relativity, he spent that looking for a unified theory that didn't involve quantum mechanics. He thought it was incomplete because it was not fully predicted. So the idea of there being uncertainty to him meant that it was a failure as a theory. So to me, that's just not really a problem. Like, completeness is not something that seems to me natural, doesn't feel natural. And it doesn't seem mathematically natural, because I grew up in this era, not in Einstein's era. So Einstein grew up in the late, 1800s, early 1900s, and there's steam engines and trains and printing presses and everything is mechanical and stuff. But I've grown up with quantum mechanics, first of all, but also with Gödel and Godelian completeness, which was happening at the exact same time as Einstein's life. So when you have Gödel, you have the idea of uncertainty built into mathematics and incompleteness. So to me, it seems silly to argue about, oh, maybe we can eliminate the uncertainty from chemistry or the physics part of things. No, why would we expect that? Because in math, you have a different kind of uncertainty. And Godelian incompleteness just comes from two simple things together. Do you have algebra? Well, we're probably going to want that for physics and stuff. And do you have Boolean algebra? Do you have true or false built in? Because once you have this statements and true or false statements, you very quickly get to the statement, this is false, which is not true or false, right? So you've broken the logic system that you completed, so that you tried to make complete. So I don't think completion is something you could have in a physical system of theorems. It's a human longing, it's a philosophical idea, and it's beautiful. I mean, it's what helped statistical mechanics. Like I said, I'm probably going to do a statistical mechanics theory just because I think it's so beautiful. It's so beautiful what's going on with ensemble averages. But it's not everything that could, it is everything that could possibly go on, but in a very specific way of statistical mechanics at equilibrium and stuff like that. Or, okay, fine, there's non-equilibrium statistical mechanics as well. Yeah, as I very well know. Okay, so we're going to get on to the next homework question. I've said enough about why I think Einstein's wrong here, why the Einstein Podolsky paradox is wrong. EPR, Rosen, right? Not to forget that guy. But you can resolve it to your satisfaction. Did I say any others? A lot of right answers. Yeah. No, for me, it's just not a problem because I don't expect completion. And it's weird to look for it on no other reason than I think it should be there. So let's see. Oh yeah, so question 3. So examine the Dirac equation and explain the Feynman-Stuckelberg interpretation, standard model component that it is. It's antimatter moving backwards in time. So I told you last time to focus on the eigenvectors rather than the eigenvalues for this. And that is just because you see the time dependence right up there. And if you go and you look up propagator mechanics or whatever, get that behind my ear, then you can figure out pretty quickly that that's just what's being implied up there, as long as you assume mass has to be positive, and otherwise that's the only things that can be changed up there. So my general thought is that maybe mass can be negative, and if mass is negative, then the energy there is not negative. It's a negative of a negative. It's a positive, and everything's moving forward in time, even though they have different relationships in the exponent there. So you can read that paper somewhere else. As I mentioned, you should. But for now, we are going to share screen. Share screen to here, the lecture. Welcome again. Oh yeah, and you should like and subscribe and yeah, comment, etc. If you have questions. You know, I'll get the notes or whatever from the comment. Here is the paper I was talking about, negative mass solutions to the Dirac equation move forward in time, in case you wanted to hear more about that. But let's go into presenter mode. I figured out what I was doing wrong last time. So old man has had success. I linked in here to the simple notation and advanced notation solution, again, to this question of perturbation theory on the kernel. And yeah, so just Google it. You can look at the answers. They're cute and they're right. So it's a nice, just like with the first one, I would say do both these questions and make sure you appreciate why they're beautiful answers. Yeah, and like I said, I don't think that completeness is a real thing to expect out of math. I don't know. I mean, granted, we're constructing it, so you could feel like you haven't done a complete job if you didn't construct all of it. But how do you know how much is all of it? Anyway, and yeah, as I was mentioning, again, this is easier to say when you're looking at it. Focus on the eigenvectors because you can see that if you just make m negative, you have the exact same relationship with respect to time and the I. And that's what you need for the directionality of time. Yeah, and the other reason we broke off, I mentioned we broke off from the last book, Griffiths. I really love Griffiths, of people that I reached out to talking about this and developing this theory. He was very, very helpful. He had lots of interesting thoughts. Yeah, he mentioned, you know, how I was talking about how the mass could be negative. He mentioned about how the I could be negative. So that was cool. I hadn't even thought about, his point was about, I didn't even have it on this deck, but it was really cool. It was about how Schrodinger didn't, with that minimization, there's a plus minus that comes in with the minimization. So why should it be whichever one it wound up with? I thought that was interesting, and I did anyway. So I love Griffiths as a person, and I love that book. That's how I learned quantum mechanics. So you should learn it that way too. But that's a different direction for quantum mechanics. That's a historical introduction, and nobody does the direct. Nobody does the antiparticle stuff historically because they messed it up kind of bad a couple times. And the only reason he got credit for it so fast is, number one, really smart guy. Did a lot of other good stuff, just like Einstein, right? He didn't get his Nobel Prize for the thing he's most famous for. He did a lot of stuff. He got credit for something. It's kind of like a cumulative award for some people. But for this specific thing, I kind of feel like we got trapped in amber. We got trapped in Dirac's 1932 understanding of this positron when he was just in 1931 so wrong. And so let's check out a little bit more in detail. He got, like I say, like he thought it might be out there. He was talking to people at conferences. Everybody loves Dirac, so everybody heard about it, including Anderson. Anderson Labs looking for it up on the mountain here, and they find it in 1932. Boom, see it in the bubble chamber. It's there. I mean, there's no, you look at, you can figure out what you're looking at pretty quick there, and you're looking at that. So they definitely had a positron, not a proton, right? It was positively charged, but with the mass of an electron, because you can tell the stuff's going through the chamber and bending proportional to its mass. So if something is 1,000 times different, it's going to go, one of them's going real thin and one of them go real curvy. And that's how you can tell it's like 1,000 times different, real curvy. So these chambers weren't like super mathy, but they were still pretty easy to tell what's happening. Bubble chambers, I forget if that's the exact one, cloud chambers, precursors to these, but basically they're going up to the top of mountains, putting up little chambers ish, and catching stuff from the sky that essentially is meant to have no interference coming straight from the sun. But I mean, obviously it could be a couple different absorptions and re-emissions from there, but you know, aside from that, and that's less likely, each order of magnitude for each time it happens. Okay, blah, blah, blah. Besides the antiproton, the thing he did wrong, and that some people still do, is the Dirac seat. So this is used for the holes in semiconductors and stuff, because there it's right. I mean, there is a bunch of places for electrons, and sometimes there are holes. And so it is right as a model for some things. but as a model for a new particle, it is not right. And when it's wrong, it needs to be addressed. So that's kind of, like I say, we've retconned it a little bit because it's correct for some things, but it wasn't right for this. And it's wrong in a bad way for this. Like when you introduce the idea that, oh, this isn't a new particle, it's a hole in a bunch of, in like an entire world of particles that are just negative energy. That's a whole world of things you've introduced, man. Don't do that. That's a real big problem. Don't do that. It's bad for every time you find a new particle, you're going to say, oh no, that's not a antiproton. It's a proton in a sea, like in a Dirac sea of, it's a hole in a sea of protons. Did I do that right? I don't know. Whoa, such a bad answer from this guy 1 year before the answer that we are taking as still right, that I think we need to really worry about this. And so I think we need to do better and not take Dirac so seriously, even though he was a super serious guy who knew really a lot of math. Yeah. So like I say, I went on this rant the page early. I got this one in me at any time. I can rant about how I don't like this. Dirac C, real bad, fine for semiconductors, fine for some things that have holes in them, but bad when your holes are not holes. Bad when your holes are real things that are different, that are not this. I mean, okay, so an antiparticle is related to an electron, but one antiparticle is not a hole in a sea of an infinite amount of electrons. Bad, 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 bad. Don't do that. Okay, so I can't yell about that enough. Don't make a negative energy C that's full unless you have it. Okay, and you can check right now. Do you have a negative energy C? If you go bang, 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 can you get a bunch of free electrons or not? Because you going bang, bang, bang gives the energy to knock them out, work functions and stuff. So anyway, you can tell if it's right or not. It's not right. So, okay. This is really, yeah. So in a different branch of physics that I've really abruptly transitioned. Oh, right. This is kind of a lead in that high energy physicists freely exchange mass and energy because of mass energy equivalence. It's a big deal. And so knowing it's true, you can extrapolate a lot of things. But we need to know more than just that E equals MC squared, because E equals MC squared is cool, big booms, did a lot of cool stuff for us. But it comes from here, it comes from the Dirac equation. So I probably should have led in with, this is how the Dirac equation leads to E equals MC squared, right? That's the way to make this a linear slide instead of a crazy way that I think slide. But as you can see here, you have the norm of the equation we were just talking about, and then broken down into operator form as you go down to the full form of the Dirac equation. So you can just see at the top, when you have this in norm form, yeah, E equals MC squared when P equals 0, right? And I mean, to me, it's really obvious because we already have the case when mass equals 0 solved right. When mass equals 0, we have the absolute value sign on the momentum. But when P equals 0, math different now. Math different now. Now, instead of absolute value on the M, we just get regular MC squared. No, math still same. Same math says still absolute value M. So anyway, it's helpful sometimes to be a tutor for middle school algebra when you're looking back at stuff. Okay, so Feynman-Stuckelberg has this interpretation of time. Matter I'm going to mess up this animation 10 times. All right, now matter going forward in time, antimatter going backwards in time. Wasn't that cute? A nice little animation. I stopped doing these because nobody really cares, and it's really me yelling at you that's carrying this. If you're still listening to it, you don't really care about the slides. You're probably reading them though, hopefully. So this is the Feynman-Stuckelberg interpretation. It was implied by the Dirac eigenvectors and stuff, but they made it explicit. They had a reason for it. They needed they needed the arrows in the diagrams, right? So they had to say explicitly what was happening, where Dirac could and did and had been fudging. So if you want to, you can call it the Dirac Feynman-Stuckelberg interpretation, but that gives Dirac maybe a bit much credit. And like I say, maybe gives Feynman too much credit, but Feynman is a physicist idol. We've been talking about idols. I'm going to try to keep addressing that because it's important for you to know me a little bit when you hear about what I'm saying. And so you can drill in on where my weak spots are and where my blind spots might be. For instance, I love Feynman. So when I look into gravitation, obviously I'm going to figure out what he did and try to make it right, because he was right about everything else. So when he came into this, maybe it was just the wrong time. He didn't have the right tools. He had a wrong idea. He wasn't willing to get rid of something like that. But he's great. Everything else, he's great. I've loved everything he's ever done. And so whatever he did here, you better read it. And so anyway, that's your homework for tomorrow, is to read lectures 1 through 3 from Feynman's Lectures on Gravitation. Because what he did here, number one, not very much. So we can read it and go over it in these 6 hours, which is a lot of hours. And you'll read an extra 5 or whatever if you actually do all the homework. But his lectures, his approach, so it's the way you want to do it. He's got the appropriate amount of reverence for paradigm. He doesn't get trapped in it, never. He just uses it for his own ends and then gets out of there. And doesn't ever, he did a good job with Einstein of not hero worshiping him, like the opposite of that when it comes to general relativity, and I wind up agreeing with him. So I won't go too much on about it. But yeah, people will agree that like everybody makes mistakes is really what Feynman's used as an example of in general relativity, because he messed around for like 10 years and basically wound up convincing no one of his theory. And to this day, because he didn't win that fight, the fight remains more or less uncontested between general relativity and quantum mechanics. Right now, there's everybody pretending that we're singing Kumbaya in the Standard Model somehow with dark energy in there too. I don't really see what's happening. But yeah, one thing I did mention is that we can understand a lot of him in this course. So he didn't do that much. I mean, we're only talking about this for 6 hours. This guy did this for 10 years. Anyway, now there's obviously 10 years of my life. I've done stuff that is very trivial, advances forward. And I understand that you can hit some ridiculous roadblocks that last a long time. And he did. He hit an unnormalizable graviton that seemed really hard to deal with without negative mass antimatter. But he had antimatter moving backwards in time. That was his own cool thing. Perhaps that's the only thing he couldn't see through, right? Because this became part of a paradigm. And I think that was part of the problem for Feynman, is he was part of inventing this paradigm. And once you're the guy who's on the name, right, Feynman-Stuckelberg, you don't really want to be the guy who is overturning the apple cart, because you're the apple cart. So why be both guys, right? You don't want to be, he was a revolutionary, but once you've done your revolution, you don't want to keep doing revolutions, right? I mean, that's just like, I'm not trying to do like theory 2 after this negative mass antimatter. Somebody else going to do that, man. I'm done with it after this. So I fully get Feynman not coming back to it. But I think that it's underappreciated in the public, and it won't be after this lecture because I'm going to put a bunch of keywords in here. But the Standard Model has antimatter moving backwards in time. Let me just talk to everybody about that and say it a little louder. The Standard Model, the thing that every physicist believes is true, thinks that antimatter is moving backwards in time. So that every antimatter particle you see is coming from the future. Hi, oh, there he goes by. He's going to the past. Cool, well, I'll tell you about it, right? No, there's no experiments ever to be done. There's no reality to this. It's just a model. So anyway, I think that's a little bit ridiculous to me. Like, hopefully we have some normal people in here and not just a bunch of physicists. If you're a physicist, I'm sorry. I know that this is very important to you. I promise we're keeping QED. I promise we're keeping quantum theory. I'm not one of those guys that's reinventing all of quantum mechanics. I'm on the team. But this is no good. Philosophically, stuff does not come from the future to be here for us now. This is like a separate anthropic principle for every moment in time that you meet antimatter, right? It's like, well, that one had to be there, coming from the future, going to the past, right here where I needed it, right? No, it's coming with you. That's why it's there. It's going forward in time. Okay. It's so crazy to me. I can go on about this a lot. This was the first thing I figured out about this. It's currently the most famous thing-ish of what people give me credit for. But what a weird thing to do, right? You have a math trick that makes stuff go backwards in time, and then you're happy with it because all the math works out. And like, as far as I'm aware, people are not really like publicizing this in lectures and stuff. Like, if you're a big Standard Model guy, you don't start off the lecture saying, hey guys, look at all this stuff going backwards in time. Cool. No, they pretend it doesn't exist, right? That's the whole thing. Not very much antimatter. If you're pretending that our local matter antimatter ratio applies everywhere, right? Because right here, table made of matter, like me, I made of matter. If it wasn't, big problem, right? If you hit matter with antimatter, explosion, big problem. Yeah, we'll go over that later. It's a real big explosion. It's a real big problem. But anyway, so you can't introduce stuff just to make math work, like antimatter going backwards in time. That's just so wildly big of a deal. Okay. But everybody indulges it. I should say why people indulge this, right? If I say it's so crazy, because the transition elements are amazing and they're right. So Feynman diagrams essentially made possible entire new perturbation theory within like path integral quantum mechanics, applicable everywhere. Lots of math can be churned. We can crank, we can crank, we can crank. The pair is a new paradigm. Like I said, he invented it. He's great at it. He did a lot of it. Other people doing it. Really great stuff. QED, like one of the best theories we've got. There's a reason the general relativity people can't get rid of QED, because this is as good as anything they got, right? They're happy about the perihelion of Mercury or whatever. Well, the QED guys are happy about the magnetic, anomalous magnetic dipole, right? So, but my point is both of these are obscure things. We need to get these guys agreeing about the big stuff. We need to address where they disagree. So my point of this slide, though, was QED is fine, right? No. It's great. QED is great. I do need another slide on that. I have another slide on that. I forgot the slide. It winds up unifying everything, right? So it's missing gravity, sure, and it's missing the strong force. But electroweak unification is a big hint to me, a big hint that everything unification, right? There's no general relativity and weak unification. There's no general relativity and electromagnetic electromechanics unification. You only have the electroweak unification. So I think that suggests, hey, stuff is like that, and you just need to figure out the ways in which the other things are like that. So yeah, I mentioned that Feynman's an idol of mine. This is so beautiful. I think it's got to be too beautiful to be wrong. I will say that this is also known as the Glashow-Weinberg-Salam model, and I know for sure that Weinberg rejects this, and for a different reason that Glashow rejects this. So even though I love them, they don't love me. Okay. So yeah, strong force is hard. You're not going to get very much from me on that. Not in this lectures at all, but I have a little theory on that. You can go read about van der Waals dispersion. But so I'm focusing in this lecture series and in general on the unification of gravity and quantum mechanics, which is not actually hard math. Like here I am in my house just doing it without a whole lab of people or whatever. You can see the homework for next time. You saw the kernel thing from last time. We'll do one more thing with it now for next time. But eventually we have a problem, as any good scientist does when they're challenging a paradigm and path integrals are diverging here. However, as I thought about recently when I was trying to get comfortable with this, that's a problem for path integrals. They diverge. I mean, it's a very specific type of path integral that doesn't diverge. And we may be able to fix it by making our path integrals like the ones in electromagnetism, which don't have to be soluble in a general form either. They're soluble when you have a divergenceless magnetic field, right? I mean, you have these statements that made those problems solvable. So what if we have a net zero charge, right? Or whatever the same, we can have similar conditions. Anyway, so I think we can fix it. So let's fix it. Next up. What's going on with this slide? Okay. Let's see if it goes 2 slides. I clicked a bunch of times. Okay, yeah, now I got a little historical aside, because I don't know what happened here. We're going to have it for homework. There's this guy, M.L. Good, professor at Harvard, right? So this is why I don't understand it. He had a model of the meson. Mesons are one quark matter, one quark antimatter living together in a little particle. And so mesons are half matter, half antimatter. Meson, if you know your Greek, Mesoamerican, right? Middle America. It's like the middle. So let's see. Blah, 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 blah. His model of the meson was right. He was saying that, okay, hey, if one of them has negative mass, then that should mean that it has a different energy from the other one, very slightly. And as a result, you should see CP violation. So when you see this thing, which doesn't live that long, decay, you should notice it decays one way instead of the other, because one way means that because one way would have a slight, they're not entirely the same energy level. So people got sad, like they didn't like his derivation, and he got, I gather, shamed out of Harvard or whatever. He didn't last as a guy much longer. Nobody cited him, and they went with the CKM theory, which came 2 years after this. So it came 2 years after this, and it wasn't cute. It wasn't nice like this. The reason, so yeah. So the reason that they didn't like Good, no, everybody understood that model, right? That if one of them has negative mass and they're both in the field of the Earth or some field, they should feel a different splitting. One of them should be pushed, one of them should be pulled. So everybody understood the argument. The point was, what field? Because it wasn't the value of the Earth's field, that they had already measured it good enough that they knew it wasn't Earth. So they didn't know what gravitational pull or push was causing the splitting, right? And when he introduced it to his model, he knew that. And so he said, okay, it's some field that's big. And that's why they didn't like it. They didn't like absolute fields for the same reason Einstein didn't like the cosmological constant. Nobody likes absolute fields that come from nowhere because they're kind of baby town. They're kind of like outside the model, fixing it, right? You don't fix it like Einstein wanted it to be flat, fixing it, you know? So they didn't like that he had kind of fixed it to make it work, but he didn't have a cosmological model, right? He didn't say, what if we have no, well, they didn't have cosmology back then at all, but what if he didn't have symmetry breaking to undo? So yeah, but now that we do, let's undo symmetry breaking and see if we can get some good thoughts from it. Yeah. So like I say, we're going to read it in for homework. You can see how Feynman addresses this. It's his number one. He says, this is the most direct evidence we have that antimatter does not have negative mass, is that we do not see CP violation in mesons. 1963. Okay, cool. That's like right after ML Good. And then what happens in 1964? They find CP violation in the meson. So I just want to go to everybody back then and say, what happened here? I don't understand it. I just don't understand it. Like Feynman, what happened here, bud? You, every other place, you're so good at this. How did you never, like, did nobody, I guess nobody brings it to you, right? Like, this is a kind of tiny thing to most people, but this is like number one, you'll see in his book on like whatever chapter it is. It's his first example of why we know antimatter doesn't have negative mass. It's these Meson experiments. I mean, first, second, third, right after Eotvos probably. So I don't, yeah, this is wild to me. It's his second example against negative mass after the Eotvos experiments, which are not a convincing example to me. Nobody goes back to the model. Nobody goes back. They find CP violation. He predicted it 3 years before it happened. CKM didn't predict it. They can model it if it happened, but they didn't predict it, right? This guy said it should happen. If it happened, like if these have negative mass, if antimatter quarks have negative mass, then there should be CP violation in mesons. We find it. Nobody thinks about that. I can't think of a different, I can't think of another example like this, where a guy predicts a thing, it happens, and he's given no credit for it, and nobody gives him a Nobel Prize. I'm flummoxed. I've talked to people about it who were there back then. He's like, oh yeah, that model was wrong, right? Yeah, that model was wrong. No, that model was not wrong. You guys got it wrong. You got it wrong because you wanted to feel smart. Anyway, so my apologies to K&M, who did win the Nobel Prize, and I'm just so sorry to Kabibo, who didn't win the Nobel Prize at all, even when everybody was patting people on the back. They didn't pat him on the back. Okay, so we got to go over this a little bit. Why are we not patting Kabibo on the back? He invented half of this model. He invented the idea that if you had an off diagonal eigenstate, that it could create CP violation in the observed diagonal eigenstates. It's a beautiful idea. K&M adapted that to the specific situation of the quarks. I think everybody deserves the prize. That's a beautiful idea. If you think that idea is right, you should give everybody. Mind-boggling, Kabibo. I apologize to you. From every physicist who was weird and bitchy to you with that Nobel Prize, I acknowledge you. And the name of the theory acknowledges you as the rightful third partner in that Nobel Prize. Okay, so the theory is basically, I already talked about it, the idea that the up and the down eigenstates don't quite match, like their real eigenstate that quark world lives in isn't quite the same eigenstate that real world lives in. Real world, quark has to live here, but actual quark lives here. It's just, get out of here, guys. Look at all these numbers. We're introducing 1, 2, 3, 4, 5, 6, 7, 8, 9 new parameters. They shrink it to 5 or whatever. And then they feel good about it being whatever, 5 independent parameters. I never feel good about this. You introduce 5 parameters to deal with one problem, and then you wonder what's up. Real bad. I mean, slip. Honestly, for me, I give the Nobel to Kabibo, and I tell K&M to take a walk. This is a bad theory. But anyway, like, we can identify a big problem, right? Okay, so we've changed the whole dang world, and we have these off diagonal eigenstates. Well, that's great. That's cool. Now, Where else should those guys be? Everywhere quarks are, right? So what about in protons? There too, right? Right? So in quarks, they would have this off diagonal that should be doing these transitions, right? Oh no! Do protons not decay ever? Like famously for the lifetime of the universe or longer, never ever decay to anything? Huh, interesting. As you can tell, I'm very mad about this. I think CK&M theory should have never been embraced. This is obviously wrong in a way. I want to curse about this, man. I know I shouldn't on YouTube, so I'm not going to. But it was wrong, not really an idea. It's a parameterization that could have fit any result in the 60s or 70s. And whoever it was, I guess, needed their grants to work, whatever. It's an everything matrix. There's no possibility of invalidation of the CKM model. Could have validated any model. And it gave us an immediate philosophical, it immediately engendered a wrong result. It's called the thing I was just describing about how the proton never decays, but you would expect it to if CKM was right. It's called the strong CP problem. But that is, even though it has the word strong in it, too tiny of a language for me. I'm so mad about this. It's just a wrong nothing idea that was never right. Yeah, I've already talked about this. I think it's so silly to overlook C. I love you, Kabibo. You should all love Kabibo too. K&M, also good. Like I said, this is beautiful. You deserve a Nobel Prize for it, but you're wrong. Yeah, I would love to find out what happened here. I'm not going to get in touch with these Nobel guys because nobody's ever going to do that. Nobody's good. People don't get back to you when you talk to Nobel laureates. Yeah, like I said, they had a less interesting model with more parameters that didn't explain what was going on. So mad about not. If my legacy is one thing, it will be the appreciation of ML Good. He was an incredible, incredible man for that model. That was right. He was right. He was proven right in his time, and he should be recognized in my time. So anyway, for your homework for next time, we'll get into some more stuff next time. I promise I will not just talk forever this time. We have reached the end, but start reading chapters 1 and 3. I think 2 is statistical mechanics. We'll do that in the other lectures. But lectures on gravitation, or maybe it's more GR than we need. Oh, statistical, great. Then I want you to derive the E equals MC squared from the Dirac equation. I want you to take the square root and tell me where the algebra is going wrong, because you can do it. If you had, honestly, this is pre-algebra stuff, man. They made a big mistake here and you can figure it out. Number 3, explain Sakharov's philosophical resolution. So we have the negative Dirac C argument idea. There's another philosophical resolution from Sakharov that's also beautiful. You should know about it. And 4, this is fun. So think about microscopic reversibility, which is a chemist's concept, and the physicist's concept of detailed balance. And think about whether or not those are related to the idea of a negative energy solution. Could it be that the negative energy solutions are just all of the reactions that are happening, that lead to the equilibriums we observe, that lead to excesses that are, yeah, I think these two might be the same concept masquerading as each other. So let's think about that. I have a lot to say about that one. So let's hold off for now. Yeah, no, this is nothing. All right, well, I'll see you guys next time. And thank you for joining me. Like I said, click, subscribe, comment if you have kept all the way to here. Honestly, if you've done this homework, shoot me an email. And we will go over it together. Yeah, have a good one. Where's the... Bye.